There is another way to represent vectors. Let's think about the x, y plane. So that's x and that's y. Now I've talked about how we can represent a vector, origin, as an arrow. So a line with a direction and a length. So we might imagine, say, we describe this vector by the length and the angle to the x-axis. So that would be some angle, say theta, and some length r. Okay, so we know how to do that. Now, but there is another way of describing vector which is also very useful, and that is, if we imagine having this arrow with its tail at the origin, then we can describe its tip position using the x and y values on this graph. So let's suppose that this x value is 3 and that y value is 4. So instead of describing it as r using r theta, we now have 3, 4. So I can describe this vector. Let me call this vector A, an arrow. So I can, but originally, right, let me write this out. So originally, we say that A is a vector with a length r and direction theta to the x-axis. Okay, all right. So that was one way of doing it. Now we have another way of doing it. We are going to say that A is equal to. Now I'm going to draw it. There are different ways to do it, right? One way is to draw large bracket and write the x and y values, x and then the y value below it. Now we call this a column vector. So that looks like a column, and we have the two numbers x and y in the column. So in this way, this can also describe the vector, because if you think about it, if you know the numbers 3 and 4, we can plot it as a point on the on the xy graph. And if you remember that the rule is to draw a line joining the origin O to this point, then we have our vector. So it's an equally good way of describing a vector, and it has other advantages. Now let's, for example, let's look at our displacement. Let's think of this as displacement vectors. Suppose that I have a ball which I move starting from the origin to this point. Now from that point, suppose that I want to move the ball in another direction there, okay, by a certain distance. Now this time I shall describe it using this new way of the x and y values. Now I'm going to describe this vector by thinking about let's say the x distance that it has moved. Let's say it has moved by a distance of 2 in the x direction, and it has moved down, meaning in the negative y direction, by -1. So I am going to think of this as a vector that I can write as 2 units to the right and 1 unit downwards, so a -1 unit along the x direction. So just to be very clear about this, it means that this vector moves 2 units this way, so that's 2, and 1 unit downwards, so that's -1. So therefore, I can describe the vector using this column vector with the two numbers 2 and -1. So now I have this vector which I shall call I shall call that vector B. Okay, I have my two vectors now. Now, so as before, suppose now that I want to add the two. So I want to add vector A to vector B. So what is the answer? Now we know from previous examples, okay, we know that the resultant is just the line joining the start position to the final position. That's our resultant, which I call C. Okay, A, B, and C. Now, but this time it is actually very easy to find this displacement vector C in terms of its x and y value. Let's see how to do that. Now, when we go from the tail of A to the tip of A, we move in the x direction by 3 units. Okay, and then we reach the tip of A. And from the tip of A, if we now move along the vector B, from the tail of B to the tip of B, we move to the right by 2 units. So that means that overall, for this vector C, we must have moved to the right by 3 units plus 2 units. Okay, 3 units plus 2 units. So that's let me write this down. That would be 3 units plus 2 units would be the y value. Let me get ready a column vector bracket here. And for the y direction, when we move along vector A, we move up by 4 units. But if we then move along vector B, we move down by 1 unit, or we move by -1 unit. So overall, we would have moved 4 minus 1 units. So that's 4 minus 1. And once we have this, we can quickly find the answer. 3 plus 2 is 5, and 4 minus 1 is 3. So there we have our C. That's actually C. 5 units to the right, 3 units upwards. Now if you look at this, the 3, 4 here is actually from A, and the 2 minus 1 is actually from the B. So what we have actually done is we have simply added this column vector for A to that column vector for B. So it makes finding this final answer for C, this final vector C, really easy, because previously we had to actually take out our ruler and protractor to actually draw a scale diagram of this triangle and then measure the final value of C, the final distance and angle for C. But this time we simply add the x and y values together. So let me finish off this part by giving these numbers some name. Now if I look at A, I've been calling this the x value and calling 4 the y value. The proper name for these numbers of a vector, this x value is called the x components, and that y value is called the y components. Alright, and since x and y, since direction x and direction y are at 90 degrees, they are perpendicular to each other, we call these two components, we describe their relation by saying that they are perpendicular. Let's see, perpendicular perpendicular components. So these are perpendicular components. So what this means is that perpendicular components are really useful, as you've seen. So if we know the perpendicular components for A and B, we have just seen that we can simply add the separate components and get the final answer if we want to add two vectors.